So still the other one. So here is the example. So we have a mixture of fine aggregates. I want to see everyone working. And coarse aggregates. And the moisture content for the fine aggregate is 2%, and for the coarse aggregate is 1-3%. So this means that these aggregates are at what state of moisture? Are they oven dry? No, they are air dry. So when it doesn't say, you always assume that the material is air dry. So we want to find out how much water you need to bring the mixture to saturation. Remember these plots? So here we have oven dry, air dry, where you have some water in the pores, and then you have saturated surface dry, where the pores outside are completely filled with water. And then we have the moist, where you have some excess water also on the surface. And this is super important because if you are in this state, the aggregates first absorb water before having the water ready for the workability of concrete, for example. And if you are at this state, the aggregates are going to release water to the mixture. So it's important to be able to understand and correct for that when you design, for example, a concrete mix. So the first thing is basically to calculate the oven dry rate for the fine aggregate and the coarse aggregate. So this is the definition of moisture content. So you see the weight that we have is air dry. So what you need to calculate is W sub S, which is the oven dry. Does anyone have the number?
I get 100.3.
That's correct. And this is in pound, I believe. Checking. And then, Dimitri, do you have that also for coarse aggregate? 150. Thank you. It cannot. Oh, yeah, it is correct. It should be a smaller. That's true. It should be a smaller than, thank you. It should be a smaller than the air dry because, of course, if you add water to aggregates, you are going to have, I have the numbers, but it's in the PowerPoint, so I need to check it there. I don't have them here. So the oven dry should be less than the air dry, because if you add water, so you are going to add to the mass. That's some way to check. Now, how do we find out how much water to add? So if you look at the moisture content definition, basically what you have here is the weight of water, isn't it? So if you subtract from the air dry or moist, if you subtract the oven dry, what is left? The weight of water. So we want to see how much water to add to bring the fine aggregates from 2% to 3.4%. So the amount of water, basically, so moisture content is the weight of water over the weight of solids. So if you want to bring the material from 2% to 3.4%, then basically, I can write it like that. This is how much you want to change the moisture content if you multiply this by the solid weight,
this will be the amount of water in pound. So I'm basically writing this MC times WS equal to WW. So the weight of water is the moisture content times the oven dry weight. Super important. Not any weight, oven dry. So if I want to change, to know how much more water I need to add, I need to just consider how much I want to change the moisture content, right? And this is something that you need to do when you design concrete. What do we get here? I think it is 1.4, but let's check. 1.4 pound. So calculate it for the coarse aggregate on your own. And then at the end, the amount of water has to be sum of the two waters that we calculated. Pay attention that if you had more than, let's say, 3.4% in the aggregate that was delivered to you, then you had to subtract. And you will see that in the examples and in the concrete mix design. So now we have deficiency. You need to add water to get to the saturation. You could have the condition if you had 5%, if your aggregate was delivered with 5%, then you had to consider 5 minus 3.4, and that would be the amount of water that you would have to subtract from the water that you would calculate for workability and other properties of concrete mix. Is that what I said makes sense to everyone? So what do we have here? So the same thing, the weight of water here also would be basically here would be more like the change in moisture content times WS, and here we want to go from 1.3 to 3.8. Someone has the number?
3.93 pounds.
3.9 sounds correct, thank you. So the total water, basically, then you have to add the fine aggregate plus coarse aggregate So this means that if you were using these aggregates for concrete mix, whatever water you calculated for your design, you need to add this much to that water to make sure that first the aggregates come to saturation. Now, I write it down just to make sure everyone follows me. If, for example, the moisture content of the coarse aggregate instead of 1.3, this is an if scenario, was, let's say, 5%, just throwing a number, then the weight of water released to the mix, this is the water, what we calculated before is the water that the aggregates absorb. And that's why we need to compensate for it. Now, if it was 5%, then the weight of water released would be 5 minus 3.8. And whatever number you would get here, you would have, this is for mixed water, whatever you calculated from your design, you had to subtract this
to calculate the final water. Otherwise, your mixture would be too watery, and then your concrete may not be as strong as you designed it for. If you have too much water, it's not good. So it may be plus or it may be minus. Here is plus, this is what you need to add. Here would be minus, what you need to subtract. Is there any question about that, what I just said? It's simple, but clear? Great. So with aggregates also come different definitions for a specific gravity, something we talked about last time, and this is what we want to review next and do an example. Did everyone copy this? Do we need to stay here one more second? No? Okay. You have it on YouTube, so there is. I'll upload it again on YouTube. Okay. So, because of the moisture, the specific gravity of aggregates is actually moisture dependent. So last time we learned that a specific gravity is like a relative density. You divide the density of the material by the density of water. But if you have different states of moisture content, depending on how much moisture you have, of course everything would be different. And that's why there are different definitions. It's kind of obvious, and it's just what I told you, that when you have more moisture, your aggregates become heavier. This is because water has some weight, so it adds to that. So let's look at these definitions. So the names are kind of, it's not very intuitive. So these are kind of the definitions that engineers have come up with. To me, they don't look the names very intuitive, but this is how it is. So apparent specific gravity, and this is the definition. You divide the dry weight, so WS is the dry weight, like before, and then volume, you divide it by the volume not accessible to water, and then you also divide it by the density of water, as we did before. What does it mean? It means that you have the volume of solid and the volume of impermeable voids. So those are the voids which do not have any opening to the surface. Water cannot really get into these which are inside. So the voids outside are not included. So that's what VI is for. So here you have the volume which is not accessible to water. So you include the volume of voids which are inside the aggregates, the ones that water cannot get into. That's the definition. And this is called apparent specific gravity. Next, definition. Bulk dry specific gravity. Again, you have dry weight, but here you also take into account the volume of pores which are permeable to water. So all the volume. And don't forget, this is the density of unit weight or density of water. And there is one more, which is bulk SST. This is very similar to the previous one. And here you have SST weight instead of having the open dry weight. So you have the weight of water and the weight of solids. But in terms of volume, it's the total volume. And this is, for example, one of the parameters that you will see in concrete mix design. These are definitions. So the best way to learn them is, I guess, doing an example. this is kind of a summation, a summary of all these together. In your formula sheet for the exams, etc., of course, you can write this down. This is not very intuitive to memorize or anything, no need for that. Now let's do another example. So we have a sample, basalt, and you see it has 510 grams in its natural state. What does natural state mean? Air dry, exactly. So when you hear natural state, think air dry. And after you put it in the oven, it loses the moisture and it becomes oven dry, 505. And then you soak it in water after 24 hours, which means that it's completely soaked and saturated. Typically you measure the weight and you wait until the weight is not changing anymore. That means the material cannot absorb more water. That's what saturation means. And then it is 560. Now, let's calculate different parameters so we practice the things that we learn and we can kind of use the equations. The first parts are easy. Absorption capacity. So look back what this parameter is. And I have made a, you have a slide like this, so it can help you maybe to put the numbers underneath each state. Just look at the pictures and put the weight under each one, so it makes it for you easier probably to calculate. So absorption capacity, we have defined this before. If you look back at your notes, you see. So that's the difference in moisture content between the oven dry and SSD state. And then you have moisture deficiency and water release. So let's get started. Work together in groups. Calculate the moisture contents. Write down the weights underneath each state like that. Doesn't matter. So it is larger than SSD, then it is moist. If it is smaller, it's air dry. So they're both kind of at the moist state. Doesn't matter the support. Work together. Look back at your notes. So I see a lot of you have it. I have calculated the moisture content and natural state, and also the capacity, which is basically pretty much like moisture content at viscosity. So it's about 2.2%. Don't have numbers like 2.1876. In the lab, if you are taking C57, you see that things are not like that. So 2.2%, just having one digit after decimal point. I know, but are you taking C337? No, I hear you, but so the effective absorption is the difference between the moisture content at SST and the natural. So that's what it is. Because when you get the aggregates in natural state, it's kind of how much they absorb until you get to the saturation. I kind of like you to have this image of the aggregates at different state in your mind. I think that's very helpful, always. Okay. Now we come to calculating the specific gravities. These are the formulas, if it helps you. And what you have is the apparent specific gravity. You see the formula. You also have the dry weight. So start from there. Then you are going to be able to get the volume of the aggregate, which is not accessible to water. That's a very good start. The density of water is 1 gram per milliliter or cc. You don't need them individually. Right? So this is Vs, this is Vi, and the volume of pores outside is V sub P. You can start doing this. I go back. So these are the definitions of Vs is just the volume of aggregate. Let's say if you had a way to separate it from the impermeable void. And then Vp is the volume of voids which are around the aggregate. Think about this picture. Have this in your mind. One thing which is easy is if you use the apparent specific gravity, you can get Vs plus Vi. Now the question is how to get Vp. Think how you would get the weight of water in those voids. If you know the weight of water in those voids and you know the density of water, you can get this volume. This is how you would go about it. Again, to get Vp, first calculate W sub P. That's the weight of water in those voids. If you know the weight, you know the density of water, you get the volume. It doesn't matter. So if the weight No. It's always on the outside. The difference between air dry and SST, look at this. It's a little bit less, so those pores are not completely full. So if you use that wouldn't give you the full volume of those pores. That's the delay that happens.
That's when you were talking about this picture, I thought you drew arrows. Oh, so water can get into that. So
Water cannot get into Vi. Look at the arrows. Those are Vi, right? And then we have Vp. Look at the arrows here. Yeah? Is it clear?
Yeah, I didn't use the not accessible water.
No problem. So the weight of water, what you want is to subtract subtract oven dry from SSD. And the reason is you want to get all those voids filled with water. If you subtract the natural state, they are not complete. You don't get the fully filled voids. Because in natural state, they are like halfway filled, right? We want to know if you fill those voids up with water, how much water it is. And the weight is just subtracting the two, 516 basically minus 505. And then, of course, then to get Vp, you need to use the density of water, and then you have this. And once you have that, then you can just substitute. Here will be 505. Here you have 200.4 plus 11. Don't forget this one here. It's 1, but it's not 1 in all units. So the numbers, just with one digit, 2.4. 2.44. And there was a question about using the term rate and weight density and mass density. If you are given in mass, just go with mass density. If you are given weight, which is less common, go with weight density. If you cancel out anyway, doesn't matter because you are basically dividing two quantities. So So it's just important to be consistent. In practice, people normally work with pound. They don't work with pound force or newton. It's just kilogram. That's how you buy things. It's like when you weigh yourself, you get pounds. You don't calculate really the pound force. But we call it weight. So, any questions about this? Move on. So if you are taking the lab, you see that there is ASTM procedure. I don't go through it more than this, but basically you use the submerged weight we talked about last time. You submerge the sample in water, and the scale is here. You measure the submerged weight, and then you can calculate different parameters using dry weight, SSD weight, and submerged weight. And for fine aggregates also there is another ASTM standard, and you are going to have a little bit different procedure. This is for the lab, so I don't go through it, just that you have it for completeness here. Okay. Now, the last part of this lecture is about gradation, pretty much. So, we talked about it a little bit last time. It's important to have appropriate grading for a lot of applications. So if you have good grading, your packing is better, it affects the amount of void. So here you can compare, if you only have coarse aggregate or fine aggregate, the amount of void is much larger than if you mix them up. So then the fine aggregate flow in the spaces between coarse aggregate, and your pore volume would decrease. That's natural. In the very, very ideal world, you want to have every single size between every single size aggregate. So all the voids just completely feel like that. But as you know, aggregates don't look like models, and they have irregular shapes, and our world is not ideal by any standard. So then we need to find a way to measure the gradation of the material we have. And if you are taking soil mechanics, you have seen this before. You have sieve analysis, again ASTM, American Society for Testing and Materials, a procedure to do that. And here you can see the sieve numbers and opening sizes in both inch and millimeter. And the number pretty much says how many openings you have in 1 inch. Those are how they look like. If you are working in the lab, they never look that clean and shiny. Absolutely not. Yeah. For a smaller size, it's number of divisions per inch. For larger size, the distance in between. Yeah, I should have said that. But anyway, you don't need to memorize it. There is always a table you can find out. And the way you do it, you stack them from the large size to the small size, big size. As you can see here, kind of old-fashioned, telling by the hairstyle. And then you basically use some sort of vibration to make sure that there's no aggregate stuck anywhere. How many have done sieve analysis? Or have seen it? Okay, a good. But don't worry, it's very simple to do. So you add the aggregates, and then after a while, so this is the modern, this is kind of how it looks like. So you shake it up to make sure that the material is not a star. And then you have different amounts of aggregate retained. So you have the aggregates passing when it goes through, and then you have retained. Like that. And with sieve analysis come the gradation curve. This is after you do that, you take every sieve, you've done it, it's perfectly sieve 7, and you weigh individual, how much is retained on individual sieves. This is how you do it. This is how you did it in the lab. Yeah. And as you can see, this is how things look like in the lab. And you may have seen this before also. Have you done the gradation curve also? Also maybe in soil mechanics, depending on if you are taking it. But it's very simple. So on the x-axis, you have the sieve size. It can be in millimeter or inch or sieve number. And it is logarithmic. And on the y-axis, you have linear scale, and this is percent passing. So that's the only kind of thing you need to be careful about. It's not percent retained, right? So the largest size here, everything passes through. So 100% is going through. And then as you go to the smaller size, you have less and less percent passing. And that's how a gradation curve typically looks like. We have 3 more minutes, so maybe we can start at least. So this is one example that I wanted us to do together. So typically when you do the analysis, you don't use all the sieves. You may just use a selection of the sieves, depending on your application. So here we have used a few sieves. The sieves number and size are here. You open it. And then what you know is the retained, because that's what you have weighted on the scale. And now the question is how to get to the gradation curve. How to start from here. So you need to kind of set up a table. Typically this is how I would do it. So your start is cumulative weight retained, which is nothing else but you say, okay, the first one is 0, the second one is 30, but the other one, you sum up all the sieves above it. So it is, if you didn't have those sieves, everything else would be depending on that. This is something that I want you to do on your own, and we don't have time. Now, the homework also has some questions on gradation curve. You can submit the homework on Tuesday if this is something new and you cannot do it. So the deadline was, or the due date was on Monday. If work on the other questions, you can submit it on Tuesday because we finished it all on Monday. And the quiz will be on Wednesday. I'll send an email. So have a nice holiday weekend.